Welcome back, grade 10s. In today's lesson, we are going to carry on learning about electrostatics. Now, in the last lesson, we ended off by discussing how charge distributes differently on conductors and insulators. What we're going to be discussing in this lesson applies only to conductors. So we're going to be talking about conducting spheres, where spheres are these perfect three-dimensional circular balls, and all the conducting spheres that we're going to be discussing are going to be identical to one another, meaning that they're made of the same material, they are obviously the same spherical shape, they are the exact same size, so that when they're made to touch and then they separate, the charge on them is shared between them equally. Now, I'm going to take you through some scenarios that demonstrate this, but it's just going to use simple whole numbers, no units of measurement, just for demonstration purposes. So let's look at the first scenario. In scenario 1, we have two identical conducting spheres, one that has a charge of -5 and one that has a charge of -15. So that means that they both have an excess of electrons because they're both negatively charged. This sphere over here at -15 has a stronger negative charge than the sphere over here. Now, the system as a whole has a total charge of -20 because -5 minus 15 equals -20. So when these two spheres are made to touch and then they separate, this -20 gets divided equally between the two spheres so that each sphere now has a charge of -10. Let's consider scenario 2. In scenario 2, we have a positively charged sphere and another positively charged sphere. Now, this positively charged sphere has a larger positive charge, meaning that it has a larger deficit of electrons relative to this sphere. Now, when the two are made to touch, the total charge in the system is +20. So that means that there is a deficit of 20 units of charge in the system. And so when the two spheres are made to separate once they've touched, they're going to share in their deficit. So now they're each going to have a charge of +10. In scenario 3, we have one sphere with a positive charge of 5 and another sphere with a negative charge of 15. So sphere number 1 is positively charged, so it has a deficit of electrons, and sphere number 2 is negatively charged, so it has an excess of electrons. Note that the excess is greater than the deficit, so we would therefore expect that once they've touched and separated, the charge on each sphere will be negatively charged. Now, if we look at the system as a whole, the total charge is +5 minus 15, which gives us a -10. So when they separate, they are going to share in this total charge of -10, and they're each going to have a charge of -5. And in the final scenario, in scenario 4, we have a negatively charged sphere and a positively charged sphere again, but in this case, the negative charge is a smaller value than the positive charge. So that means that in the system, there is a small excess here, but a large deficit here, which indicates to us that once the spheres have touched and been separated, they will both have a positive charge because they're going to share in the deficit, which is larger than the excess over here. The total charge in the system is -5 plus 15, which is +10. So when the two have separated from each other, they are going to share in this deficit. So they will now each have a charge of positive 5. Now, when it comes to forces between these charges, recall that like charges repel and unlike charges attract. When we consider these conducting spheres, if we have two conducting spheres that are negatively charged, they will obviously repel each other. If one conducting sphere is positively charged and the other one's negatively charged, then there'll be a force of attraction between them. And anytime you're given these questions, you will be told that the conducting spheres are on insulated stands or on an insulated surface or hanging by an insulated string. And the reason for that is we don't want the electrons, whether in excess or in deficit, on the conducting spheres to distribute themselves on the stands. We only want them to be on the spheres. So when two conducting spheres on insulated stands touch each other and then they're made to separate, they will share in their charge evenly. Now, charge is represented by the letter Q. So if the initial charge on the first sphere is Q1 and the initial charge on the second sphere is Q2, then the final charge on each of the spheres would simply be calculated as Q1 plus Q2 divided by 2. So remember that the charge per sphere, once they've been separated, is going to be the same for both the spheres because they are going to share in their excess of electrons or in their deficit of electrons equally. So in this formula, Q1 is the charge of sphere 1 measured in coulombs. Q2 is the charge of sphere 2 measured in coulombs. And once we've divided that value by 2, then we would get the charge per sphere, also measured in coulombs. Let's take a look at an example. Metal spheres A and B on insulated stands are brought into contact and then separated. Calculate the net charge on each sphere after separation. So note that we have to work in coulombs. Our values here for charge are given to us in coulombs, so we do not need to convert. Note that both sphere A and sphere B have negative charges. B has a larger negative charge than A, which means that it has a larger excess of electrons than A. So we need to apply the formula Q per sphere equals Q of sphere A plus Q of sphere B divided by 2. We're just taking an average of these two values. So that's minus 4 times 10 to the minus 6 plus minus 8 times 10 to the minus 6. And that answer divided by 2 gives us a new charge of minus 6 times 10 to the minus 6 coulombs. So these are the original or initial charges on sphere A and sphere B. And once they've been made to touch and separate, their new charge per sphere, meaning that both sphere A and sphere B will have the same charge of minus 6 times 10 to the minus 6 coulombs. Now let's talk about charge quantization. The basic unit of charge, called the elementary charge, represented by QE, is the amount of charge carried by one electron. The principle of charge quantization tells us that every charge in the universe is a multiple of the charge of a single electron. I'm going to explain what that means. The charge of a single electron is this value over here, which is given to you on the formula sheet. It is minus 1.6 times 10 to the minus 19 coulombs. So if I have a conducting material and it is made up of 1,000,000,000,000 electrons and 1,000,000,000,000 protons, then the net charge of that material is 0 coulombs, because the number of electrons is balanced out by the number of protons. Now, if I put one extra electron on that sphere, what will be the charge on that sphere? Well, it will have this value over here. And if I add another electron to that sphere, what will be the charge on that sphere? Well, it will be double this value. And if I now add 10 excess electrons to a sphere, what is the charge on that sphere? Well, it's 10 times this number. Now, because we don't get half an electron or a quarter of an electron, we don't get a fraction of this number. So anything that has a charge has to be a multiple of this number over here. So all charge must be a multiple of this value. Any negatively charged object has this value over here, or a multiple of this value. Now, if an object is positively charged, then it would have a value of the same number, except that now it's a positive value, or a multiple of this value. So going back to our neutral sphere, which has got 1,000,000,000,000 electrons and 1,000,000,000,000 protons, making it neutral. If I now remove an electron from that sphere, it now becomes positively charged through one electron deficit. So the value of charge of that sphere, it will be positive, and it will have this value of positive 1.6 times 10 to the minus 19 coulomb. And if I've removed 3 electrons from my neutral sphere, then it will again have a positive charge, and the value of that positive charge will be 3 times 1.6 times 10 to the minus 19 coulombs. We may calculate the total charge as the number of electrons, whether in excess or in deficit, multiplied by this number, which is the charge of one electron, if we have an excess of electrons, or this number, which is the charge of one proton or one electron in deficit, in the case of a deficit of electrons. Using this formula, Q, big Q, meaning the total charge, is equal to N, which is the number of electrons, whether in excess or in deficit, times QE, which is elementary charge, which is the charge of a single electron in excess or in deficit. So this QE value is a constant. So in this formula, Q is the total charge measured in coulombs. QE is the charge of a single electron. And N is the number of electrons. It must be a whole number. It doesn't have a unit of measurement. It just represents the number of electrons that are in excess or in deficit. If you find this concept confusing, let's look at an analogy. So let's say we have 4 babies and each baby has a mass of 3 kilograms. That's equivalent to us saying that we have electrons and each electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. So if I have 4 babies, each one with a mass of 3 kilograms, what is their total mass? So the total mass can be calculated by the number of babies multiplied by the mass per baby. There are 4 babies, each one with a mass of 3 kilograms, so the total mass of the babies is 12 kilograms. In the same way, if I have 4 electrons, what is the total charge of these 4 electrons? Well, the total charge can be calculated as the number of electrons times the charge of each electron, which is exactly like the formula we just saw in the presentation. Big Q, the total charge, is equal to the number of electrons times the charge of one electron. So the total charge would be based on 4 electrons multiplied by the charge of each electron, which would give us a total charge of minus 6.4 times 10 to the minus 19 coulombs. Now let's look at it another way. If the total mass in a room full of babies is 150 kilograms, how many babies are there? Now this total mass over here must be a number that's divisible by 3 kilograms, which is the mass per baby, because we don't get a fraction of a baby, we only get whole babies. So the number of babies is equal to the total mass divided by the mass per baby, which is 150 divided by 3. Now remember that the 150 is measured in kilograms and the 3 is measured in kilograms. So the kilograms cancel each other out. So when we work out the number of babies to be 30, it's just a whole number. There is no unit of measurement. It represents the total number of babies in the room based on the 150 kilograms that all these babies total in mass. Now, in the same way, if you're given the total charge of a system, you can figure out how many electrons there are in the system. The number of electrons is equal to the total charge divided by the charge per electron. N is equal to Q over QE is the formula that we just learned. So the number of electrons can be calculated as the total charge divided by minus 1.6 times 10 to the minus 19. Now, because my total charge here is negative, that means that I need to divide by negative 1.6 times 10 to the minus 19 because I have an excess of electrons. And this answer here for number of electrons must always be a whole number. And it must always be a positive number. If the charge here was a positive value, you would divide by positive 1.6 times 10 to the minus 19. The reason being that you have a deficit of electrons, and you must again always manipulate the number of electrons to be a positive number. Now this charge over here is measured in coulombs, and obviously this charge over here is also measured in coulombs. The two cancel each other out to give us a number without a unit of measurement as an answer. And again, remember that this answer must be a whole number because we don't get fractions of electrons. We only get whole electrons. Let's now look at some examples to make sure that we've grasped this concept. An object has an excess charge of minus 1.92 times 10 to the minus 17 coulombs. The fact that it has an excess negative charge means that it has an excess of electrons. How many electrons does this number, does this total charge relate to? Our formula is Q is equal to N times QE. But recall that we're trying to figure out N. So we may rearrange the formula as N equals the total charge divided by the charge per electron. So that's minus 1.92 times 10 to the minus 17. Remember that if the big Q is negative, then we are going to divide by a negative 1.6 times 10 to the minus 19. And that will give us 120 electrons, which is a positive number, and it is also a whole number. Two identical metal spheres have different charges. Sphere 1 has a charge of minus 9.6 times 10 to the minus 18 coulombs. Sphere 2 has 30 excess electrons. So the first question that we're asked is to calculate the charge on sphere 2 based on the knowledge that it has 30 excess electrons. Our formula is the total charge is equal to the number of electrons times the charge per electron. Now, because we have 30 electrons that are in excess, then we need to multiply 30 by negative 1.6 times 10 to the minus 19. And we get a total charge of minus 4.8 times 10 to the minus 18 coulombs. So that means that sphere 1 has a charge of minus 9.6 times 10 to the minus 18 coulombs, and sphere 2 has a charge of minus 4.8 times 10 to the minus 18 coulombs. Sphere 1 and sphere 2 are now made to touch, and then they are separated. What is the new charge per sphere? So now we need to apply the formula Q per sphere equals Q1 plus Q2 divided by 2. And these Q's over here represent the total charges. So that is minus 9.6 times 10 to the minus 18 plus minus 4.8 times 10 to the minus 18. And we divide that by 2, so that now we can identify that the new charge per sphere is going to be negative 7.2 times 10 to the minus 18 coulombs. So sphere 1 started with this charge and ended with this charge. And sphere 2 started with this charge and ended with this charge. How many excess electrons are now present on each sphere? We just calculated that the total charge on each sphere is this value over here. So we need to work out how many electrons this value equates to. We're going to apply the formula N is equal to Q over QE, where our total charge is minus 7.2 times 10 to the minus 18, and we divide that by the charge of an electron, and we end up getting a number that is positive and that is a whole number, and that represents the number of electrons that are now present on each sphere once they have been separated from each other. This question comes up very, very regularly, and the question is, how many electrons were transferred during contact? So the first thing that we want to do is figure out how much charge was transferred. And once we've calculated how much charge was transferred, we can equate that total charge to number of electrons. So again, this is a commonly asked question, and our first step is to work out the charge that was transferred from one sphere to the next. And the change in anything, in this case the charge being transferred, results in a change in the charge, is always the final minus the initial. So to calculate the amount of charge that was transferred, we look at the final charge minus the initial charge. And we can do that either for sphere A or for sphere B. We would actually derive the same answer regardless. Remember that the final charge is common to both spheres, because once they have touched and been separated, they share in their charge evenly. And like I said, we may use either initial charge and we will derive the same answer. If you look at this drawing, because it really helps to have a drawing, sphere 1 has an initial charge of minus 9.6 times 10 to the minus 18 coulombs. And then we were told that sphere 2 has an excess of 30 electrons, which we calculated to be equal to a charge of minus 4.8 times 10 to the minus 18 coulombs. And once these two spheres touched and separated, The charge, the final charge on each sphere is now identical at minus 7.2 times 10 to the minus 18 coulombs. So we're going to use final charge minus initial charge for sphere 1, or final charge minus initial charge for sphere 2. And that would allow us to work out how much charge was transferred. And once we know how much charge was transferred, we may then work out the number of electrons that corresponds to that amount of charge. So let's take a look. If we're going to use sphere 1, and we're going to use sphere 1's initial and final charge. So the charge that was transferred is the final charge minus the initial charge. So it is this value over here minus this value over here. Now, don't forget that you're subtracting a minus, and a minus and a minus makes a plus. And so the charge that was transferred is 2.4 times 10 to the minus 18 coulombs. Why did we get a positive charge? We got a value for charge transferred that was positive because the charge was actually transferred from sphere 1 to sphere 2. Remember that sphere 1 has a bigger charge, so it has a greater excess of electrons. So the charge was transferred from sphere 1 to sphere 2. The reason we get a positive value here is because sphere 1 gave up electrons to sphere 2. Now that we have the charge that was transferred, we may apply N equals Q over QE to calculate the number of electrons that that charge applies to, and that would give us the number of electrons that were transferred from sphere 1 to sphere 2. The total charge we just calculated is 2.4 times 10 to the minus 18. Remember that N, the number of electrons, must always be a positive number. So because here we're dealing with a positive charge, we are going to divide by positive 1.6 times 10 to the minus 19, thereby making sure that the number of electrons that we derive is a positive number. And we also need to make sure that it is a whole number, which it is. So 15 electrons were transferred. Now we can do it using sphere 2's charge, in which case we would say that the Q transferred is again the final charge minus the initial charge. It is minus 7.2 times 10 to the minus 18 minus 4.8 times 10 to the minus 18. Now we're going to get the same number of coulombs, but in this case it will be negative, and that makes sense because sphere 2 received electrons from sphere 1, so it gained electrons. But regardless, the total charge that was transferred is the same value. Again, it is negative because sphere 2 gained electrons. And now that we have the total charge, we may calculate the number of electrons that it relates to. But over here, because we have minus 2.4 times 10 to the minus 18, so our charge transferred is negative, we are going to divide by minus 1.6 times 10 to the minus 19, so that the number of electrons is a positive number. And again, we need to make sure that it is a whole number. And note that we get the exact same answer regardless of which final and initial charge we use. In the next lesson, we will learn about polarization, and we will go over past paper questions.